Hope you had a good lunch. Hopefully the rain wasn't too bad as well outside. We have a great talk now on attacking V8 by Ayman. Let's welcome Ayman to the stage.
Hello everyone, hope you had a good lunch. Thanks for coming to this talk. My name is Ayman. I'm a senior consultant at CyberCX. I'm based in New South Wales, been there for almost the past decade. I presented last year in BSides Sydney, much smaller conference than this one, on ransomware development, and this is my first time to present here in Canberra. I've been attending BSides Canberra since 2016, but it's my first time to present. I started my InfoSec career as a pen tester, but I also enjoy exploit development and reversing and malware and vuln research. I have a couple of CVEs and a few exploits that I wrote in the past. Today I'm here to talk about a research I did last year in my own time. This is not what I do during my day job. Long story short, a CVE came out for a vulnerability in Google Chrome with reports of it being exploited in the wild. So I had some confidence that this is an exploitable vulnerability and decided to study it, because why not, right? This presentation is to document and share with you the journey of going through this research. It's going to be a detailed technical presentation. There will be JavaScript. If you're a front-end developer, you may like it or not, because the scripts don't look like they make much sense, but they will when we examine how they are processed internally. It's okay if you didn't follow along with every single slide. I will be doing recaps with key takeaways every while. First, a childhood story. When I was a little kid, I enjoyed playing video games, and I was always fascinated with game trainers or cheats and always wondered, how do they work? On my old computer, I came across a cheat engine that lets you create custom cheats. Basically, what it does is it searches and edits the memory of the game process, and it worked like this. I run my game, and let's say I have 3 initial lives. I switch to the cheat software and search the game's memory for the value of 3. It will find several results. I go back to the game and kill the character, so the lives count decrements to 2. I switch back to the cheat software and search within the previous results for a value that has changed from 3 to 2. This will narrow down the results within the memory space. Rinse and repeat until you find the memory location of the desired variable, be it lives or ammo or whatever, and set it to an arbitrary value like 99 or something, and then I play the game. This could be one of my earliest experiences with computer hacking, which I like to define as manipulating computers, or more specifically software, to behave in a way that was not intended by its original developers, and exploit that to our advantage. So today we're going to talk about a modern software, much more complex than DOS games, and that is V8. Not the car engine, we're talking about Chrome V8. Not that either. So what is it? V8 is a JavaScript engine created by Google, and it powers Google Chrome and Node.js. What's a JavaScript engine anyways? Here are 2 sets of programming languages. What do you think each set have in common? Languages on the left are compiled, while the ones on the right are interpreted, which are slower but more flexible than compiled languages. Where would JavaScript fit? It looks like an interpreted language, right? We do not compile it into a binary executable as we do in C. Instead, we execute it from within a browser or another runtime environment like Node.js or Electron. So, is V8 the interpreter that runs JavaScript? Well, it's a lot more than that. Long time ago, JavaScript was used in small scripts to perform simple tasks like form validation. Then with the rise with complex applications like Google Maps, interpreting JavaScript became too slow, and there was an essential need to speed up execution. The JavaScript engine is the runtime environment that enables browsers to execute JavaScript, but also in an optimal and efficient way. It employs just-in-time compilation and various optimization techniques to improve the performance of JavaScript execution. This is a list of different JavaScript engines. V8 is Google's JavaScript engine. It's the one used in Chrome, Node.js, and Microsoft Edge. SpiderMonkey is what Firefox uses. Chakra was an engine developed by Microsoft and used in legacy Edge browser before it got rewritten upon Chromium. JScript was the old engine used in the old Internet Explorer browsers, and there are other lightweight engines that can be used in embedded systems. This is how V8 executes a JavaScript. First, the script code is parsed by a parser that produces an abstract syntax tree, which is a representation of the script in the form of a tree data structure. It looks like this. The abstract syntax tree is then fed into a component in V8 called ignition, which produces a bytecode that is a machine-independent virtual machine code similar to Java bytecode or .NET intermediate language. Ignition executes or interprets the bytecode, and as the bytecode runs, V8 monitors the execution, collects information, and may decide to optimize some code by throwing it to another component called turbofan, which is an optimizing compiler that takes the bytecode and compiles it into faster native machine code. Occasionally, the optimized code may become invalid, and V8 will need to fall back, de-optimize, and then re-optimize again. This cycle goes on as the JavaScript executes. Ignition and turbofan is the modern execution pipeline in V8. Previously, they had different components named full code gen and crankshaft. And at some point, they had a mixture of both pipelines together, and they called it Franken pipeline, which was very convoluted. Full code gen was the baseline compiler and compiles JavaScript into native unoptimized code, and crankshaft was the old optimizing compiler. But these are now replaced with ignition and turbofan. V8 also introduced a mid-tier compiler called Sparkplug, and it's another compiler that sits in between ignition and turbofan. It produces non-optimized native code. This can be useful because optimization itself is an intensive process, and we also need to collect enough information before even deciding to optimize the code. Ultimately, the goal is to achieve high-performance JavaScript execution rather than producing the most optimal code. So Sparkplug is a middle ground between the slower bytecode interpreted by ignition and the heavily optimized code produced by turbofan. In this talk, we are only concerned with a few of these components. Just know that ignition interprets bytecode produced from the JavaScript source code, and turbofan is the optimizing compiler that converts bytecode into native machine code. To demonstrate ignition, let's read this simple function. It takes 3 arguments, A0, A1, A2, and does some arbitrary processing on them. We add the first 2 in a local variable, x, decrement the third argument and store the result in a second local variable y, and then return the product of these 2 variables. Now here's the equivalent ignition bytecode of this function. Let's step through its instructions. First instruction, load accumulator, which loads the second argument, A1, into the accumulator register. We add the first argument, A0, to the value stored in the accumulator register. Store the accumulator register into R0 register. Load argument 3 into the accumulator. Subtract a small integer of value 1 from the value of the accumulator. Store the accumulator into R1. Load register R0 in the accumulator register. Multiply the value stored in R1 times the value stored in the accumulator, storing the result in the accumulator, and finally return the value in the accumulator register. The takeaway here is that this is an internal virtual machine, a register-based VM inside V8, and ignition is the interpreter that executes our JavaScript in the form of these bytecode instructions. If we call a function enough times, it becomes hot, and to cool it down, V8 sends it to turbofan, the optimizing compiler, which produces a native machine code shown on this slide. Let's also read the assembly code. No, I'm just kidding. We're not doing that. Okay, with that brief background, let's get into the vulnerability we're researching, and we'll introduce further theory as we go. From the NIST website, it says there's a type confusion in V8 that allows potential exploitation of heap corruption. Brief interruption about type confusion. You may have seen this meme before. An interviewer asks a question, what's 2 plus 2? The interviewee responds with 22. Surprisingly, the interviewer acknowledges the answer. Not very surprising to us. It's obvious from the quotes that we're talking about strings or characters. But the point is, the type of data is a very important context, as it determines how will the computer process them. Addition of value of 2 as an integer is going to be processed through an arithmetic operation, while adding 2 as characters will be string concatenation. Back to our advisory, it lists some external reference links. One of them is the Chromium bug tracker, crbug.com. This link lists further details and even provides a proof of concept code that triggers the bug, which is very useful. It states something about leaking the whole value. At the time I was researching this page was not public yet, which would have been around Q3 last year. That's why also on the list page it says permission required for this page resource. So let's pretend we haven't seen it for now. What we can see in the URL is a bug tracking ID, 1450481. V8 is an open source project. We can look up this ID in the source repo, and we find some merge requests. One of them has been merged into the main branch. Looking at this merge request, we get a nice diff between the old code and the patch. The patch added checks for some conditions. If the receiver is JS arguments object, and if it has fast packed elements, if these conditions are met, the store fast element built in is called with the standard store for the store mode argument. That's a lot of information. Slowly, but first we need to set up our dev research environment. We need to get our hands on a vulnerable version, unpatched version of the software we're researching. Referring to the advisory, it states V8 in Google Chrome prior to some specific version number. We want to find an earlier version number. Unfortunately for us, Google does not allow download of older software. There are third-party archives, but we cannot trust those. Also remember that we are only concerned with the V8 engine rather than the entire browser. Google blog shows release history where we can look at previous version numbers. Let's pick one earlier than the patch update. There used to be a tool, online tool called Omaha Proxy that I used to find which V8 commit is associated with a particular Chrome version. This tool is no longer available, but there is a current alternative called Chromium Dash. And it does the same thing. We can go to Chromium Dash, look for our desired Chrome version, and find the V8 commit from there. Now that we know the commit that we want, we start setting up our environment. To download and build the V8 from source, we use the dpot tools published by Google. Follow this procedure to clone the repo and roll back to the unpatched V8 commit. After checking out the old commit, we should verify that we actually have the old code by looking at the affected files, just a sanity check, and we find that our code indeed lacks those newly added checks. We continue to build the repo. It's going to take a while to compile, maybe an hour or two if I remember correctly. After compiling V8, how are we going to use it? I initially thought that I would need to link V8 against a test program or something to start using it, but luckily V8 comes with a great tool called D8, which is immensely useful. It's a shell where you can execute JavaScript as you do in the web browser developer tools. You can also pass it a script to execute, or execute a script and then drop in a shell. D8 also supports powerful commands known as the native syntax that we can use inside JavaScript source to greatly assist with debugging. For example, we can debug print a variable or an object or a function to print debugging information, and this is how I got all these screenshots on the slides. We can also break execution while running D8 under a debugger, and many other commands. You can run D8 ---- help to get a list of different switches. With V8 compiled, we now can start our analysis. First, we want to understand what the vulnerable code does and how do we reach it. We see that the patch is in a function called store element handler in the keyed store IC class, and this code is in a source file called ic.cc. IC is short for inline cache. Quick recap. We have V8, an interpreter, ignition, whose job is to quickly turn the source code into unoptimized bytecode. As V8 executes the bytecode, it keeps collecting profiling data. When a function gets called many times, it becomes hot. To cool it down, V8 sends it along with the profiling data to Turbofan, the optimizing compiler, which produces optimized native machine code for faster future execution. Inline cache is one of these optimization mechanisms. Our bug has something to do with it, with the inline cache, so we would like to activate it. But first, let's quickly glance over some more theory. In a programming language like C or C++, type checking occurs at compile time. When we declare a variable, we must also define its data type. For example, the C code on the left of the screen declares a variable named x and also specifies its data type of integer. This is called strong typing. Whereas a dynamic language like JavaScript allows the programmer to start using variables and assign them arbitrary data without having to worry or specify their type. This is much easier and flexible for the developer, but it offloads additional work to the JavaScript runtime. It needs to make assumptions about the data type and needs to get it right, and should also be able to change those assumptions when needed. If it makes the wrong assumption, security implications could ensue, which is what happens in type confusion vulnerabilities. C++ also requires the programmer to define classes before they can instantiate objects from them. But JavaScript allows the programmer to dynamically create objects and add members to them on the fly. JavaScript abstracts class definitions away from the developer, and to be able to do that, V8 maintains a hidden class for objects that the developer creates. These hidden classes are also called shapes, and they define the shape of the object, that is, its members and their orders or offsets. Multiple objects can reference the same hidden class or shape if they have the same shape. These shapes can transition dynamically as we add more members, also known as properties, to the objects, unlike C++, where all the members have to be predefined in the class. When we access an object property, V8 may need to perform extensive lookup operations as it walks the shape transition chain and finds the property's location or offset. In order to reduce similar future lookup operations and improve performance, V8 will keep a record of how it previously accessed that property, so that when it encounters another lookup of a similar shape, it can take a shortcut from the cached information and skip another entire lookup. This process is the inline cache we mentioned earlier in the patched file ic.cc. Let's take an example to see inline cache in action. Here we have a function, ic. It takes an object and returns 10 plus x property of that object. We call this function numerous times with an object argument. Here's the bytecode of the function. First, get named property of argument 0, then add a small integer 10 and return the value. Notice these numbers in brackets. These are slots in the feedback vector, which contain the cached information we just talked about. Slot 0 is for the small integer. Slot 1 informs V8 how to load the property x of our object. And note that it says monomorphic. This is the initial state of a feedback vector, and it means that V8 has only seen one object shape passed as an argument for this function so far. If we call the function again, but this time pass it another object with a different shape, the new shape has an additional property y this time. This time V8 finds that the object's shape does not match what it has seen before, invalidating the cached information. It performs another slow lookup for the new shape and updates the feedback vector. Now we see that the feedback vector slot has changed to polymorphic, which is less ideal in terms of performance than the previous monomorphic state. Now if we keep changing the shape of the object we pass to the function, for example here we change the members of the object argument, A, B, C, and so on, eventually the feedback vector transitions to a megamorphic state, which is the least optimal. Basically, V8 says, I've seen too many shapes now, maybe there's no point optimizing this anymore, so I'm just going to give up on tracking this any further. Okay, so our source code has something to do with the inline cache. What else do we need to know to be able to reach the vulnerable function? The function name is store element handler, and there's something about keyed store. What is that? Here we have an array. We store some values at numeric-based indices. These are called elements of the array. We can also store values at non-numeric indices, as in dictionaries or associative arrays. In V8, these are called named properties. Here is a debug print of our array, showing all the elements and the properties. Elements 1 to 3 at index locations 0, 1, and 2. We also see properties named A, B, and C with the values 61, 62, and 63. And while we're talking about arrays, let's also discuss their types. Remember we said that V8 maintains a hidden class or shape for objects. These are also called maps. Looking at the map of this array, it says packed SMI. SMI stands for small integers, meaning that the contents of this array are only of type small integers. If we add a double decimal value to the array, we find that the shape has transitioned from SMI to double elements. And if we add another object to the array, it transitions to a more generic type elements array. Okay, what does packed mean? Packed means that the array contains contiguous or adjacent elements stored next to each other. Comparing languages again, in a language like C, we can only access data within the defined bounds of the array. In the C code on the left, we have an array of 3 elements. Therefore, we cannot access or assign value at the 5th index. But in JavaScript, we can. What V8 will do is will mark the 4th index of the array as a hole between the data. Now we have enough idea about the inline cache and other V8 internals. Going back to the vulnerable function, let's start writing a proof of concept that triggers the bug. We first want to reach the vulnerable code. Here's a JavaScript function. F stores an element in an array. We keep calling this function repeatedly up to 100 times. Let's run it and watch if inline cache kicks in and reach the desired code. We run D8 under the GDB debugger and set a breakpoint in our target file. And indeed, it hits our breakpoint after 10 iterations of this loop. Great. We are able to reach the interesting function. Next, we want to write a test case that calls the function with the specific conditions that were patched. Back to the diff. The patch checks if the object is of type JS arguments and that it has fast packed elements, in which case it sets the store mode to standard store. In our test case, we want to satisfy these conditions to trigger the bug. We now know that packed elements means there are no holes in the array object. What about the other conditions? JS arguments is simply a special object available in every function that contains the arguments passed to this function. In this example, argument 0 is the first argument to the function, argument 1 is the second, etc. What about store mode? The optimized code that inline cache will produce is actually one of C, C++ functions that are baked in V8 and known as built-ins. The specified store mode decides which built-in is going to be used to optimize storage operation of that object. The patch forces the use of standard store, so we can guess that the bug must be present in one of the other cases. Let's explore the different store modes. Here we have a function that stores the value of the second argument in index 1 of an array passed in the first argument. We call this function 10 times to prime the inline cache and then inspect the generated built-in using the debug print command. We find that the standard store mode is used. And here is it under the debugger. Now let's tweak the function to trigger the other store modes. In this version, we increment the index of where to store the value, effectively expanding the array with each iteration. This time we get another built-in, store and grow, no transition, copy on write. So with each storage operation, the built-in function makes a copy of the object in a larger buffer because we grow the array. Note that it also says no transition, meaning that it is not going to transition or change the shape of the object into a different one, as according to the feedback vector, we always pass an array to this function. We haven't called it with any other object type yet. Another store mode similar to the previous one, except that it doesn't grow the array. In order to reach it, I had to perform 3 consecutive store operations. First one, passing an array of integers, packed SMI. We find that the standard store is used. Next, I call the function again, passing doubles, decimal values. The previous array of small integers cannot hold doubles, so now the array type has transitioned into a more generic type, packed double elements, which can handle both SMIs and double. We still get the standard store built in again. We keep calling this function, changing its content furthermore to characters or strings. These data cannot be represented by neither SMI nor doubles. So the array transitions into packed elements, which is the most generic elements kind that can handle other values than SMI or doubles. Throughout this script, the array has transitioned from the specific integer SMI to the most generic elements kind. Such transitions can only go in one direction, from a specific elements kind to a more generic one. It does not transition back to the specific kind like integers again. So this time we get this store mode that says no transition, indicating that the array object we're storing into is not going to transition to a different shape. The last store mode is ignore out of bound, which initially sounded like the most interesting one to me. I was able to trigger it with something called typed arrays, which are basically raw binary memory buffers. They have fixed length and specific data types. As in this example, we define a typed array of length 1 for an unsigned short integers. When we attempt to write beyond this array's length, nothing happens and the length remains the same. Hence, when inline cache optimizes this function, it uses the ignore out of bound built-in. Not that interesting after all. So it took me a while to write all these test cases and study V8 and figure out what's happening in the background. While I was doing that, an exploit got published. I got very excited. I ran it, and it crashed. But it gave me a good nudge into the right direction. Consider this array with 3 elements, 0, 1, and 2. It's packed because the elements in the array are contiguous. If we add an element to the array after a gap, here we store a value at the 5th location, skipping the 4th. The array transitions from packed to wholly type, and we see that V8 stores a special value called the whole to indicate holes within the array. Now here's the problem. We're finally going to write the test case that triggers the bug. Starting with a similar function that takes an array or object and stores some value at some index, all specified in the function arguments. We add a second function, doesn't do anything yet, but it gives us access to the JS arguments object, which is available in every function. The arguments object is empty because there are no arguments that we pass to the main function. Just note that this is a JS arguments object. Its map is packed elements, and its length is 0. We pass the arguments object to our function, call it 10 times to trigger the inline cache to optimize the function. In our function, we store a dummy value in a property of the array called BSides. Remember that unlike numeric-based elements, properties are named indices as in dictionaries or associative arrays. We do that because this storage doesn't grow the argument's length. It still has no elements, and its length remains 0. Now the function has a monomorphic feedback vector. It has been optimized for a single object shape of packed elements, which is our JS arguments object. Next, we declare an array and pass it to our function, but we write beyond its length. V8 notices that this array has a different shape than the JS arguments object, previously cached in the feedback vector. It updates the feedback vector to become polymorphic, and it changes the built-in to grow, no transition. This is the store mode we saw earlier when we extended an array by writing beyond its length. And it uses this built-in for both object shapes, the packed SMI elements, which is the second array we are growing, and also the packed elements, which is the JS arguments object we first used. Now here's when the bug happens. In this state, if we pass the arguments object to the store function again and write beyond its length, as we did in the other SMI array, the grow no transition built-in is going to be called. It will grow the arguments object without changing its map or shape because no transition. And this is a problem because now we have a packed elements object that contains holes. At the bottom of the screenshot, you can see element 0, which is the value that we wrote. And V8 grew or extended the object by placing whole values at the end, but it did not change the object shape from packed to wholly as it should have. So now our script can read the value of the whole by accessing it from the arguments object. V8 will return it to us as we are reading from a packed element object, effectively leaking the whole value to the end user. Now, what's the implication of this? The whole is an internal value. It is not meant to be known or accessible to the end user. Leakage of the whole has been exploited multiple times in the past to achieve code execution in V8. Getting fixed every time. There's now a proposal to not make such a leak a security risk in the future. If you search up V8 whole exploit, for example, you will find multiple write-ups and techniques that explain them, including this bug, all of which have been fixed by now. Okay, now let's see how can we turn this info leak of the whole into code execution. When Turbofan optimizes a function, it makes some assumptions and speculations. We can trace them using D8. Let's quickly inspect the optimization of our script before looking at how the whole leak was exploited. We run our script through D8 with a couple of flags. The first flag will produce a log of turbofan optimization steps that we can read or grep through. And the second one will produce a JSON output file that we can use to visualize using a tool called Turbolizer that comes with V8. And it looks like this. After loading the files, we get this view where we have the JavaScript source code on the left, assembly on the right, and in the middle we get a sea of nodes graph, which is a representation of the JavaScript that can show both the control and the data flow of the program. Zooming into the graph, we find the beginning of our loop. Watch the node highlighted in yellow. The loop variable is checked if it is less than a constant of 30,000, which is the number of iterations. If not, we go through the false branch and exit. If true, we load the keyed property of our object and store the value of 1. Also notice that Turbofan has inlined our function instead of calling it as part of its optimization. Finally, we increment the loop variable and continue to iterate. As you can see, Turbolizer is a powerful tool to visualize the control flow of the script and also inspect the data and their types. Now consider this function f takes a Boolean argument. If the argument is true, we return not a number, nan. If false, we return -1. Very simple. We'll add a slight change, bitwise or with 0. Nan or 0 equals 0. So if we call it with true, we get back 0. One more minus change, we add 1 to the result. So if we call this function with true, it returns 1. If we call it with false, it returns -1. Let's send this function to Turbofan and analyze it. We can do that by calling it many times, or we can use the native syntax using D8. Okay, here's our graph. We first have a node of potential values for n, either not a number, nan, or -1. The node highlighted in yellow, the top one. We see that in the data types of the nodes. We perform bitwise OR and increment operations, ultimately resulting in either the value of 0 or 1, depending on whether we call the function with true or false. So far, so good. Now here comes the trick. If we replace nan in this function with the whole value, side note, there is also a native syntax to retrieve the whole, so if you want to test it out, you don't actually require info leak vulnerability. You can just use D8, but of course you cannot do that in a real web browser. Okay, replace nan with the whole. Similarly, in the graph, we have potential values of either the whole or -1. But this time, Turbofan thinks that the output of the number function is always going to be -1. There was no case to handle the whole value because this was not an ever expected scenario. Here's the previous graph from the nan function where V8 correctly identified both cases of not a number or -1 for the variable. Now, the Turbofan incorrectly predicts or assumes that this function is always going to return 0, whether we call it with true or false, which is wrong, because if we call it with true, the return value is going to be 1, not 0. Let's try to use this incorrectly optimized value as an index to access an array. Here we declare an array of 4 doubles. The last element should be at index 3, but we attempt to read at index 4, while Turbofan thinks we are reading at 0, because it's speculated that n is going to be always 0. However, it's going to be 1 if we call the function with true. We run this, it doesn't work. We trace Turbofan, we find that it has added some bounce checking when accessing the array. The bounce checking ensures that we only read from index 0, so we need to work around that. The at method is an alternate way to access array elements. It was created to allow accessing the last element using -1 index, as in other languages like Python. Using the at method makes Turbofan skips the bounce checking step. This was actually another bug reported a while back and only got fixed last year. So we use the at method to read a value just after our array. Like this. We get an arbitrary value from memory, converted to a double because our array is of type double. Next, we're going to develop this out-of-bound read primitive into further ones that allows to perform arbitrary read-write within the memory space. If you recall today from the morning keynote, exploit primitives building, this is what we're doing next. To do that, we need to format a certain layout in memory. If we define 3 arrays like that, the first one contains some values and a second similar one, and the third array contains both arrays. Each array will be placed in memory in this order. Elements of the array at the top, followed by the array's metadata, that its map and length, etc. The consecutive arrays will look like that. Elements of the array followed by metadata of the next array, and so on. We can inspect the memory under the debugger and compare it to the debug print output. This is our first array. Here we can see the metadata of the first array starting at the map address, and then the properties, and the elements, and the length. The reason length reads 8 in memory instead of 4 is that the least significant bit is not used for data in V8. V8 uses it to distinguish between pointers and small integers. So small integers are left shifted by 1. So 4 left shift 1 is 8. This is also the reason why you see I subtract -1 from the pointer when examining memory. This is a feature in V8 called pointer compression. You can read about it further if you're interested. And here are the elements of the array, also all left shifted by 1. Now we're going to use our out-of-bound read to leak the metadata of the first array and copy it into the elements of the second array to create a structure that resembles an array header. Using this forged array, we'll be able to access the data below, like elements of array 3, but the difference between accessing the elements through that fake array or normally through array 3 is that the shape between both arrays is different. Array 3 is an array of elements. When we access them, V8 will dereference the pointers and retrieve the destination element object. While the fake array that we control, we can set its shape to be an array of doubles. This way, V8 will interpret these pointers as double values and return them without dereferencing. This is type confusion again. The type or the shape of the object determines how it is processed. The fake array is going to be useful in 2 ways. First, we can leak addresses of arbitrary objects by placing them in array 3 and reading the pointer through the fake array. Conversely, we can craft fake objects by storing a pointer in the fake array, then attempting to dereference it through array 3. These are 2 common primitives in JavaScript exploits to achieve arbitrary read-write, which is what we're going to do next. If we increase the fake array's length by editing our forged header, we can extend the array and continue reading further objects beyond array 3. This is nice, but we would like to have more powerful arbitrary read-write primitives instead of being confined to adjacent objects. Remember typed arrays that we mentioned earlier? They allow us to access binary memory buffers through array-like objects. Let's create a typed array and fill it with some values, 41s, and inspect it under the debugger. We see in the debug print data pointer, which is self-explanatory, where we expect to see the typed array contents. And indeed, this is where our 41s are stored. So if we have a nearby typed array, we can use our fake array to overwrite the data pointer to an address of our choosing, and then perform arbitrary read-write. Next, we use that to achieve code execution. When Turbofan optimizes a function, it compiles it into an executable memory region. Take a look at this function. It doesn't do anything. It only returns an array of doubles. Let's call it many times to trigger Turbofan optimization and inspect the compiled function. Here's the debug print. It shows the Turbofan generated code and also the source code of the function. Looking at the Turbofan code, we find the address of the actual assembly, like this. If we disassemble at this address, we eventually find our double values. So what we're going to do is encode our shell code in similar double values and place little jumps in between to execute the shell code. There are scripts that can do that for you. A shell code to execute binsh will look like this. Here are our double values after being compiled with Turbofan. If we start executing from the right offset within this function, our shell code manifests like this. Execute a little bit, followed by a jump, execute the next bit, and so on. All what we need to do now is get Turbofan to compile our function. Then we use our arbitrary write primitive to overwrite the instruction start address of the optimized function to the start of our shell code and then call the function. Finally, here's a recap of our exploit. We first leaked the hole. We used the hole to make an out-of-bounds read. We crafted a fake array object that allows us to modify adjacent locations. We used a nearby typed array to achieve a more arbitrary read-write primitive by modifying the data pointer. We encoded our shellcode in an array of double values. We used turbofan to optimize the shellcode and write it in an executable location. Overrode the instruction start address of turbofan code to point to the beginning of our encoded shellcode, which is going to be a known offset within the function. And finally, we execute the code. Now, I had a live demo, but unfortunately, due to AV issues, I cannot show it. But I do have a recording, which is going to be very brief. Hopefully, you can see this. Oops. Sorry. There we go. I run the 8. This is its version. It's an older version. Then I run the exploit. Boom. Drops into a shell. If you're interested in similar work, you can set up a similar playground environment, get an exploit, try to fix it, look at previous V8 exploits and study them. You can also search the Chromium bug tracker for POCs and play with them. Here's a list of links that helped me during this research. Thank you all for sitting through, and I would also like to specifically thank Kylie and Silvio for organizing BSides. Thank you.